record these lectures, so I just hit the record button. Let's see what people said. And I want to see reveal submission counts. So 13 people, so out of 21 people who answered, 13 people said linear regression, 3 people said reinforcement learning and transformers type per second. Very close third is a fully connected neural network with 2 people. So 13 people think it's linear regression, big majority on linear regression. And linear regression is the wrong answer. That is the wrong answer. If you pick linear regression, that is not the odd one out. Linear regression actually is part of the in group. 4 of these things are kind of the same kind of thing, and linear regression is one of those. So because so many people got it wrong, let me give you guys a second chance. Now you know linear regression is wrong. I'll send it back to you again. Again, feel free to discuss what does linear regression have in common with these other ones, and we'll revote. This is a common thing that happens in my classes. So let's revote it. I'm going to set this up again. Feel free to start thinking, and I'll start another timer, and we'll take it up again. Okay. What do I want to do? Okay, it's open again. I'll start a timer in a second. Even if you don't want to change your answer, you have to put in your answer again. Feel free to discuss. Do not, if you select linear regression, I will know you're not paying attention. Actually, I won't know because today's anonymous, but starting next class, I will know. Yeah, I guess I always like put in a little disclaimer, like if people get lazy and start doing things like selecting the same answer again, even though I told them it's wrong, then I say, then I will count it for if you get it right or not. But I've never had to do that, so hopefully we won't get there. So don't select linear regression, pick a different one. Feel free to chat with your neighbors, and let me do another timer for 1 more minute. All right, like 10 seconds left. There's like 4 people who still need to answer. Get in your final votes. Okay, here we go. So I'm gonna hit the button, and then it's gonna be closed, and then you won't get your answer in, and then you won't get your participation marks. Okay, let me reveal the counts. 2 people, I guess, got locked out because there were 19 instead of 21. Okay, this time, the most common one is reinforcement learning with 9, then transformer with 6, fully connected network with 4. Nobody wants to pick convolutional neural network, which is interesting. But this time, you guys have stumbled across the correct answer, which is reinforcement learning. So very good. Reinforcement learning is the odd one out. The other 4 things are all kind of related to each other. Does anyone want to say what they think the other 4 all have in common? Again, it's okay to be wrong. Your hand is halfway up.
I don't want to say the obvious possible answer, like something related to networking or pathways and stuff. I feel like reinforcement learning is doing the same thing over and over again to push the same thing. Everything else is like crazy.
Okay, got it. So you're thinking of the network part of these things.
Yeah.
And network is like things connected. But does linear regression fit into this network idea?
I was thinking more like a pathway, I guess.
A pathway?
Like
okay.
pathways, the reinforcement's more like repeating the same thing.
Okay, got it. So yeah, so I like this. I mean, you can kind of identify this. These both have neural network as the last 2 letters, like things connected to each other, maybe something like that. The only puzzle is how does linear regression fit into that? So why is linear regression like those other 2? Does anyone else want to take a guess? Yeah.
So, I think, and I'm not sure, I understand, neural networks use transformers, and you can think of a transformer as the beta vector from linear regression.
Okay, this is great. So let me highlight some of the things you said. So one thing you said is you can think of a transformer as the beta vector from linear regression. And that is the right idea for what these things all have in common. all of these things, this thing, this thing, this thing, and this thing, they all have some parameters. And when you are doing like statistics, you are on the hunt for like good parameters. And when you are playing with neural networks, you're also on the hunt for good parameters. In statistics class, you spend a lot of time on linear regression, and you're like, what is the optimal vector, right? Like, let's find it. I guess you guys called it beta. Some people call it theta, but it's some vector of all the parameters. What are you going to set them to? In linear regression, the parameters are like the coefficient in front of the thing, right? So it's linear regression. You say like, we're going to take the x value, we're going to multiply it by beta. What is the right value of beta? Sometimes you have like beta 1 times x1 plus beta 0. Those are the vector of things. All these other things also have parameters, just like from linear regression. In linear regression, the parameters have these nice interpretation as like the coefficient in front of the x value. In these things, there is no nice interpretation. They're just like weirdo parameters that combine in some weird way to give the answer. We're going to talk about that in a second. A transformer, I think you said, was like something like it's part of a neural network or something. That part is not quite right. Does anyone know what a transformer is? One possible answer is it's that movie from 2015 now. I guess that movie might be out of date of the references I'm allowed to make in the class. Okay, let's move on. Anyone want to take a guess? What is a transformer?
I know the paper name.
Okay.
Attention is all you need.
That's right. So there was a paper called Attention is All You Need from, I think, 2016 that introduced this new thing called a transformer. So that's right. Do you know what a transformer is, though?
No, but I think the original use case was natural language translation.
That's right. So it was one of these things that is used on natural language translations. We will talk about that in a second. All of this is correct, so very good. What is it? Yeah.
The thing that has the Decepticons?
It's the thing, yes, exactly, right. So that's from the movie. That's not what we're doing. Yeah, so unfortunately, I don't know why they picked Transformer. It's a weird name. But they were into like buzzwords, right? Like attention is all you need, very catchy name of a paper. And it is the thing that is used when you use ChatGPT under the hood. It's using a transformer. What is a transformer and what are all these things? These are what they call in stats or math or computer science, they call these models. So they are models. They are trying to predict something. And they all have parameters. You tune the parameters to try to make it predict the thing that you want. Linear regression is the one you should have learned in your intro stats class. A transformer is the one used in ChatGPT. These other ones are also used in other places, but all four of these things are what we call models, and it really is just a parameterized function. So it's a function with inputs and outputs, and that's what these four things are. Reinforcement learning, on the other hand, is something completely different. We're going to get to that one in a second, but let's write down what we know about these four so we can sort of get that right. Okay, let me get my blackboard open here, and hopefully this will work. Okay. Okay. This is what in stats they call a model. A model, and it is a function. Really, it is a function with parameters. Function with parameters. So classic example is the linear regression model. Linear regression. And this is the function which you input a bunch of x's and you output, let's do beta, because that was suggested. You do beta I times xi, or in other words, like beta, let's say there were two variables, x2 plus beta 1, x1. Sometimes you add on like a beta 0, like that. And that's I equals 1 to the dimension of the input. Let's say n input, the input dimension. And that is linear regression, so this is f of x, right? You tell me the vector x, I multiply all the entries by these beta parameters, I add them all together, that gives me some number, and that is f of x. If you want to be extra fancy, sometimes people write f of x semicolon beta, and the beta vector is in there as well. Sometimes people write it without the beta, and you have to know that it depends on the beta vector. So it's a function that depends on parameters, and it has inputs, x, and it has output, which is some kind of weird combination of the betas and the x's. That is linear regression. Okay. Who's seen linear regression before? Okay, great. So hopefully you've seen linear regression in one of your intro stats classes or have some kind of notion of this kind of problem. That is linear regression. The other ones are all like this, except they are more complicated. So how does it use the parameters can be extremely complicated. For example, a transformer uses it in a very complicated way so that it can do all sorts of things that seem superhuman, like reading text and summarizing text and all sorts of things. But at the end of the day, it's still a function with an input and parameters, and it uses the parameters to do something to the input and finally get an output. We'll see more examples later. So these are all models. All these things are models. All these are models, they're functions with parameters, different ways to combine the parameters to get the function. And reinforcement learning is something completely different. And I put them on a little grid over here. Let's see if I can get the little grid to open. Okay. Here's my little grid. Okay. So on the x-axis of this little table, I have models, linear regression, a neural network, a convolutional neural network, and a transformer. And on the y-axis, I have what are called learning paradigms. A learning paradigm is like a way of taking data and trying to use it to train your model. So kind of there's two ingredients when you want to do some like machine learning task. You pick a model, you're like, I'm going to do it with linear regression, or I'm going to do it with a transformer. And then you say, how am I going to take all the data that I have, and how am I going to put that into the model to try to learn something? And the simplest possible one is supervised learning. This is the one you learn in Stats 101. I'm going to go through some quick examples with supervised, unsupervised, and self-supervised learning, which are sort of the classic ones. And then at the end, we'll get to reinforcement learning, and then we're going to spend the whole rest of the term on sort of reinforcement learning and building up to it. But just so you see like what's different about reinforcement learning than sort of the classical way of thinking. So supervised learning, this is, if you do supervised learning with linear regression, that is exactly what you do in your intro stats class. All the examples there are this kind of supervised learning thing. The other example I'm going to get to is the MNIST data set, which is kind of like the Hello World data set for machine learning. I'll talk about that one in a second. But first, let's start with what is supervised learning and what does it mean to do supervised learning with linear regression? And what it is it's how do you take the function that we just wrote down, how do you use that function to do something useful? And what is the way you set it up? So that's what we're going to do, supervised learning over here. Okay, let's get this set up. Okay, so linear regression is this function, and supervised learning is this idea of let's take a data set, supervised learning. We're going to have some data set, and our data set is we're going to write it down as a bunch of x and y pairs. So we're going to say xi, yi, well, I going from 1 to the number of examples in our data set. And sometimes the number of examples is small, like 10 or 20, sometimes it's in the millions. But the point is we have these x's, and we want to use the x's to predict the y's. Use x to predict y. Okay, and if you've taken a stats class, you know these kinds of examples. Probably in stats class, they don't say supervised learning, they just say like using the data or learning or something. But it's important for us to say supervised learning so that we can distinguish it from the other types of learning. And the reason it's supervised is because somebody will tell you the value of yi and the value of xi for all your examples, and your goal is to find parameters beta so that the function from over here, that function matches well. So f of xi comma beta is approximately yi. So you want to make the function, make it so that the input, when you input x, you get approximately the thing yi that you had. It is very useful to think of a specific example, like what is the x, what is the y? Instead of making one up, I'm going to see if you guys can make one up. So this is another feature we can do with the Mathematize platform is give me some intro stats examples. So what is an example of an XY input-output pair that you worked on in your stats class where you can just make one up? Here's an example that they use a lot in stats. X is your blood pressure. So you go to the doctor and they measure your blood pressure. And then Y is did you have a heart attack? So we'll say it's 1 if you had a heart attack, say, in the next year, and 0 if you didn't have a heart attack. And it would be very nice if the doctors could figure out a way to use your blood pressure to predict if you're going to have a heart attack. That would be a useful thing for the doctors to do. So if I was going to do that as my example, I would type in blood pressure, comma, heart attack. So X is your blood pressure, and Y is did you have a heart attack? If there's an example you remember from your intro stats class, you can type it in. You can try to think of one. What is a nice example of an XY pair? Again, I'll give you like 2 minutes to think. Question or comment from Gabe? Yeah, go ahead.
Does it have to be through stack? Because I had a stack with
It does. I will not know if it was really from your stat class or not.
Okay,
Yes.
good.
Type in anything you want.
Because then I can use some
Okay.
from last semester.
Maybe I should be more careful before I tell students to type in anything they want. Okay, type. I will, like, anything you type in has a chance of appearing on the board and me talking about it. So be aware that could happen. But yes, type in anything reasonable of what you think is an XY pair of an input and output that you might try to use the X to predict the Y. What would something like that be? Okay, I'll give you 2 minutes. Yeah.
So when you shoot the table, then it gets it right down.
Yes, the table will come back many times. So yeah, don't worry. You'll get a chance to fill in your table. Yes. All right, 1 minute left. Halfway. Okay, time's almost up. Put in your final thing. Once again, today's class is all anonymous. After today's class, if you don't answer, then you will not get a credit for that thing. It is okay to answer with like, I don't know or something. That's always fine. But do try to get in before the time is up so you get your marks for coming to class and participating. And actually it does help me quite a lot. If a lot of people are saying like, I don't know, like that does help me like slow down a little bit and do things. So don't feel embarrassed to say, I don't know. Probably if you don't know, a lot of people also don't know. And that's good for me to know that you don't know. Okay, let's see, what do people say? The fun thing is this is a word cloud, so it should make a little word cloud for us over here. Okay, so looks like the most popular thing that you learned in stats class was of. All right, the second most popular thing was height and weight. This is one that is definitely a very classical example. X could be the height and Y could be the weight. Or, I guess there's a lot of like agriculture thing with like sheep and stuff. You like the length of the sheep and how much the sheep weighs or something. We also got hours, sleep. So maybe something like hours of sleep predicts how well you do in a class, or like if you're in a car accident or something. Oh, GPA, yes, that's your. So the hours of sleep could be like the X and the Y could be your GPA. Try to use the hours of sleep to predict your GPA. Of course, students that don't sleep very much tend to have bad GPAs. So maybe there's a pattern there. We can also, in a class with 20 people, we can also go submission by submission. Yeah, use your midterm grade to predict your final exam grade. The number of oil changes to predict the car life. The age to predict your height. This is a cool one. Probably the age is not very predictive of height because once you are an adult, it doesn't change very much. So this would be one where you could try, and maybe for young kids it works really well, and then for older people it does not work. So lots of interesting things. Okay, income, debt payment, things like this. Yeah, hours spent studying GPA. I guess probably more than one person did something like that. All right. Oh, hours of sleep and disease. Okay, yeah. So hours of sleep can affect lots of things. There you go. All right, amazing. Great. So let's do this one. Let's do hours of sleep and your grade. Let's do that. That's a fun example. So example. Xi equals the number of hours of sleep of student I, of sleep of student I, and yi equals the grade of student I. So our data set is a bunch of students. The number of examples we have is the number of students that we're looking at. So the number of examples equals the number of students. N examples equals n number of students. And we're trying to take this data that we've collected, and the thing that makes this supervised learning is we're doing this after we have run the test, right? We know the grade of the student. This has already been determined and is already part of our data set. So already did the test. Let's say the exam. So this is like after the exam, we collect this data set, and then maybe we try to make a prediction for next year's exam, right? And the thing that makes it supervised learning is you know the value of y. This is known. And that's very important. You'll see that in the other learning paradigms, sometimes we don't know the value of y. But if we do know the value of y, we do want the value of the function f to be approximately y. We measure how well it's doing using something called a loss function. So we have a loss function. This measures how well f matches the pattern, say. Pattern. Okay, so, and here is a classical one called the mean squared error that a lot of people use for things. You take the value of f of xi minus yi and you square it. So if the student actually scored a 70% on the exam and we think they scored an 80%, we do 80 minus 70, that's 10. We're off by 10 points. We square it. When we square it, we're off by 100 points. And the nice thing by squaring it is it makes all the negatives into positives. So if you underestimate by 10 or you overestimate by 10, that's going to be 100 either way. And we average that over all the students. So we do the sum, I going from 1 to the number of examples. And we do 1 over the number of examples. That's the average. And this is called the mean squared error, the MSE. Mean because we're averaging, squared because we squared it, and error because that's how far we are off of. And what you try to do in supervised learning is to try to make your mean squared error as small as possible. So you try to shrink this error as small as possible. What do I mean by shrink the error? Well, actually, remember, this f depends on parameters. So the f actually depends on parameters. So there's some beta over here, and the mean squared error depends on beta. And then there are many different methods you could try to manipulate the value of beta to try to make the mean squared error smaller. One classical one is called gradient descent. So you calculate the gradient of this whole thing, and you try to shrink the value of the mean squared error. There are other ways you can do it in stats class. They just make you memorize formulas. Here's the minimizer of the thing, stuff like that. You can do it with linear algebra in situations like that. But in general, that's the game. You got the mean squared error. You try to make it as small as possible as you can on the data set that you have, and you hope that the function f that you get at the end of the day is approximating the y's, and you hope that it all works out. That is basically supervised learning in a nutshell. If the function f is the linear function that we did before, then it's linear regression. So if f looks like this exact type of formula, and you use this exact kind of mean squared error, that is exactly what you learn in your intro stats class when you do linear regression. So far, all we've done is we've filled in the top left corner of that big table of different things. All of this should be somewhat review. In stats class, they kind of gloss over this kind of thing, so maybe you didn't do it in a lot of detail. But it should like vaguely ring a bell of, oh yeah, there's like data and you're trying to match the inputs and the outputs, and the function should vaguely ring a bell. Any questions or comments at this point? All right, let's go back to that big table and see what else we can fill in. So that's everything we've done so far as Stats 101. Let me give you another example that everybody does in machine learning, which is the MNIST dataset. And it's the same kind of setup, And you'll see that in a second why a convolutional network is something that will work well on it. And I think I have that here. If I do this, okay, I gotta skip over here. This is the MNIST data set. So in the MNIST data set, the X is not the number of hours of sleep. It's not even a number. It's 784 numbers, which are arranged in a 28 by 28 grid. So the input to the function is an array of 28 by 28 of either values between 0, which represents black, and 256, which represents white. And they are pictures of digits. And in fact, these are, in the 70s, a bunch of people who wrote on envelopes. They had their envelopes scanned by the National Institute of Standards and Technology, NIST, and someone modified it. That's the M. MNIST is the modified NIST. And they scanned all these like handwritten digits, and then they worked really hard to label them. So the Y values are the labels, either 0, 1, 2, all the way up to 9. The inputs are like a picture, and the outputs are a number. And the MNIST problem is you have a database of 10,000 of these digits. Can you find a function that will recognize, if you give it an image, recognize that it's a 1, or recognize that it's a 3? And this is sort of an image recognition problem. It turns out if you try to do something like simple from your stats class, like linear regression or even logistic regression, it does not do very well. So it'll have a pretty high error rate. It will not be able to do a good job of determining that a 1 is different than a 9. And the problem is it's very non-linear. Like you see, a 9 sort of contains a 1 in it, right? Like this piece of the 9, it kind of looks like a 1. So if you have a linear system that's like, hey, this looks very 1-y to me, like all the 1 neurons are turned on, I'm getting a lot of 1 signal over here, it's going to be wrong. So you need something that is able to do sort of smarter things and say like, yes, there is a part over here that looks like a 1, but there's also this like loopy bit, and that means it's not a 1. So it's definitely not a 1, don't do that. And it turns out neural networks are really good at this type of problem. In fact, this is one of the problems where neural networks were the first things to get like superhuman performance and be just as good as humans at recognizing these digits, whereas things like logistic regression, linear regression are not very good. And it turns out there's a thing called a convolutional network. A convolutional network kind of looks at different patches of the image. So it looks like this little patch and it looks at this little patch and it connects them in a certain way. And it does really well because it sort of knows that a 1 over here is the same as a 1 over there. They're just all the patches are shifted over, and it's able to sort of understand that and learn from it. So I won't go into super details on what it is, but this is a problem in a supervised learning paradigm where neural networks do really well, in particular convolutional neural networks. All right, another good place to stop for questions. First of all, who's heard of the MNIST problem before? Okay, maybe like a third of the people here. Very good. This is if you like Google like neural network tutorial or something, it'll probably be this. So nowadays you can like solve this in like 1 minute. When I was a grad student, it was like big news that people were solving this with neural networks. Okay, let's go back to our table, and we finished the row on supervised learning. So supervised learning, you have labeled inputs and outputs. You have these XY pairs. You try to learn a function that matches the X and the Y's. One thing that is hard about supervised learning is who are you going to pay to make all these labels? You need the labels. If you don't have labels, you can't do it. And so in MNIST, they like literally paid people to look at a bunch of digits and write down, hey, that's a 3, hey, that's a 1. And you have all these labels. But you can imagine in real life, that would be very time consuming and take a long time. Like if you want to do stuff with like all the pictures on the internet and label them, you're going to be there for a while. And that is why, even though supervised learning is really good for certain things, it's not good for everything. We need unsupervised learning. What is unsupervised learning? Let me show you an example of unsupervised learning. This is a picture from a paper with a student who was a Guelph undergrad student, Griffin Flatto. And we had the MNIST data set, but we ignored the labels. So we took the data set of the digits as a bunch of pictures, but we did not use at any point the fact that this one is a 1 and this one is a 3. We just had a database of images, if you will. And there was a method called a variational autoencoder where you map the pictures into like 3D space in a way that it preserves kind of the identity of the digits. So this is the mapping in 3D. And there's a little video here, which hopefully should loop. Let's see, it does a loop. Okay, great. So these are 700 dimensional vectors. There's 728 pixels. And we mapped it into 3D space. And we did it in a way, every dot over here represents one picture. And we did it in a way that all the zeros, those are the red dots, those are all zeros, all get mapped to the same kind of quadrant of the sphere. But remember, the computer doesn't know that a 0 is a 0. It just knows that all of these red things, they have something in common, right? And all of these blue things, those are, I guess, sixes. You know, the sixes are close to the zeros. Why are the sixes close to the zeros? Well, they both have a big circly bit, right? So the computer has somehow figured out that these things have something in common, these things all have something in common, and they should be sort of close together. On the other hand, the purples and the greens are sort of starting to overlap. What are the purples and the greens? Aha! The purples are 8s, and the greens are 3s. So the purples and the 8s are starting to overlap because a 3 and an 8 kind of look similar. So in this kind of work, it's unsupervised learning because we don't have the labels. And the goal is, even without the labels, can you sort of like classify the data, like group things that are similar and not similar, and what can you do with it without the labels? And in this situation, we can do a pretty damn good job of kind of separating out different digits from each other without having somebody to come in and label. And that's nice because then you can get bigger data sets from the internet and you don't have to pay somebody to label them. In this particular paper, we were working on improving out-of-distribution detection. So that's like if somebody comes in and says, you know, here's some digit you've never seen before. It's not a digit 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Could we detect that this is not in the previous data set, right? So if somebody is like, I don't know, maybe there's a different number in, like, a Roman numeral. If somebody comes with a Roman numeral and tries to write it in, we'd be like, hey man, that's not 0 to 9. That was not in our data set. It doesn't look like anything we've seen before. And in this particular work, what would happen is if you gave me the Roman numeral 2, it would presumably not be on the sphere at all. It would be like off the sphere or inside the sphere. And we would be like, hey, this is very different than everybody else. So this is unsupervised learning. What can you learn without labels? And usually it's like mapping things into a space and seeing what you can do. That's unsupervised learning. You don't have the labels. Questions or comments about unsupervised learning? All right, great. Let's go back to our table, our big table. So we've done supervised learning, where you have the labels, you try to learn the function. We've done unsupervised learning, where you just have the x values, there is no y value, and you try to like group them together or something in a way. In that paper, we were doing it with fully connected networks. So that's a type of neural network as well. Next up is something called self-supervised learning. What is self-supervised learning? Well, supervised learning is when you have the label. Unsupervised learning is when you don't have the label. So what on earth could self-supervised learning be? And the reason self-supervised learning is important is because that is exactly what is used in GPTs, like chat GPT. GPT stands for something like generalized pre-trained language model. And these are models that they literally, I'm not exaggerating, they download everything they can from the internet. So they have a data set called the pile that's like petabytes big that contains like everything ever written, like all of Reddit, all of Wikipedia, all of like these chat logs, like all of Facebook, right? They take these like giant data sets and they train these models on these whole things. And it's certainly not supervised because there's not enough humans in the world to sort of label all this and tell you what's going on. And it's a very clever way to sort of be unsupervised in a smart way. So let me show you what that looks like. So in self-supervised learning, what you do is you take some data set and you cover up part of it. And if it's language, it's a very nice analogy with filling in the blank. So imagine you have the sentence, thou shalt not make a machine in the likeness of a human mind, which is this common sci-fi trope that appears in all these different Wikipedia pages, is this sentence. Well, you treat this sentence, which you just downloaded from the internet, you treat it as a fill-in-the-blank problem. So you treat it as a fill-in-the-blank problem. If I told you the first 2 words are thou shalt, can you please guess what is the third word? And if it's, can you please guess what is the third word? I know the answer. I know the answer is not. And so I have taken an unsupervised problem, and I have converted it into a supervised problem by making it a fill-in-the-blank question. So if you can guess with high probability that the next word is not, then you got it right, and we will measure how well you are doing with that loss function. So we'll have a loss function that says, if you can predict the next word is not, then good job. Like, how likely can you make that prediction? It turns out you can't use mean squared error like we did, but you can do something pretty similar. So you can just take this data set and pretend it's sort of a supervised learning problem. Can you fill in the blanks? And this is what self-supervised learning it is. You take an unsupervised thing, but you kind of pretend that it's supervised by creating these fill-in-the-blank problems. For language, it's a very nice thing. They also do it for images where they cover up an image, right? So if you have a picture and there's half a kitten on this side, can you guess what is on the other side of the image? Well, if you're a human, you're like, well, it's probably the other half of the kitten. But if the computer can guess that it's another half of a kitten, then it has understood something about how kittens work in real life, which is that usually they have 4 limbs and not just 2. So you sort of learn something about the text, or like whatever it is, by uncovering the masked parts of the model. So in this case, it's fill in the blank. That's self-supervised learning. And that is how GPTs are trained. And they're very good at filling in the blank. They're very good at predicting, like they would have a high percentage chance of having not. The nice thing about this stuff too is if you can predict thou shalt not, then you can just do a fill in the blank on the next word, right? And if you have thou shalt not, fill in the blank on the next word, fill in the blank on the word after that. As long as you fill them in one at a time, you can keep feeding it into the model and always predict the next word. That is what happens when you do ChatGPT. It's always just predicting the next word. Technically, it uses something called tokens and not words, but it's always just filling in the next part of the sentence, and over time it strings together a big, long sentence about whatever you asked it about. So that's self-supervised learning. Questions or comments about that one? This one is highly relevant to how these modern AI things work, which I think even when I taught this course a year ago, they were not as big as they are now. Okay, so last but not least, what is this course about? It's not about supervised learning, it's not about unsupervised learning or self-supervised learning. It is about a 4th way of doing learning, a 4th way of taking data or something and trying to learn something with it, which is reinforcement learning. And I'll give you a couple different specific examples here. So that'll be the rest of the class today. We'll be going over kind of these examples to let you see what it is. But the big idea in reinforcement learning is that the data set might sort of depend on what you've learned so far. And you'll see what I mean in a second. Let me start with the first most simple example, which I think is the best example to sort of have in mind, is some kind of game. So in reinforcement learning, you can always think of these ingredients: a state space, an action, and a reward. Let me write these things down. So reinforcement learning Okay. So how is reinforcement learning different than all these other ones we've learned about before? In addition to having X's and Y's, you have actions you can take. So this is the big difference. The big thing that makes it different than everything else is actions. So the main important thing, difference, is actions. So all the things we looked at before, there were no actions you could take, right? You had a data set, you're trying to learn something about it, but there's no actions to be had. In reinforcement learning, you very explicitly have actions that you can take, and what actions you take will affect what things you see. The most common example is like robots, right? So imagine trying to train a robot to do something, like you have like a little Roomba, and you're trying to train it to move around the room. The robot, depending on how you have it programmed, will see different things, right? If you always train it to move in a straight line, it will never see that corner of the room over there, and it will never learn, oh, if you're in this corner of the room, you should do something this way. So the actions sort of affect what you see, and that is kind of a chicken and egg problem, right? Because if the robot will never see that corner of the room, it will never learn to do the things it needs to do in that corner of the room. And so this is like a problem you gotta solve. Like how do you make it take actions in a way that it will learn things to do? So robots, another example is like a robot arm, same kind of situation. If the robot arm never learns to like move this way, then it won't be able to move that way. So robots, and the other big one is games. We'll have a few game examples as we go. So in games, you take actions, and the actions affect like what is going on in the game. And if you always take bad actions, you'll never get to see like certain game states that could be very good. So you sort of want to use your actions to explore the possible things. So the 3 big ingredients, the way we're going to phrase the ingredients, and we're going to get into more detail on what exactly this is later. So this is kind of an overview, ingredients. So the 3 big ingredients you need are what I call a state space. A state space. This is kind of the answer to the question, where are we now? So for a robot, it might literally be where we are. If it's a game, it's like, what is going on in the game right now? What is the state of the game? And the state space is the set of all possible states. Okay. The next big thing is actions. So actions. What can we do? So for a robot, it might be something like move left or move right or go forward. It could even be something more granular, like apply a voltage of 2 volts to your motor number 3, right? That could be an action. So depending on how you set up the problem, the actions are the types of things you want to learn how to do, and the actions affect the state space. So what actions you take will affect what happens to the state space, and it affects how you sort of move around this state space. In a game, you might imagine if you take good actions or bad actions, good or bad things will happen to you. You'll move to states that are good or bad for you in the game. And there's a feedback loop, right? The what state you're in affects what actions you can take. So these kind of feed back into each other. So what state you're in affects what actions are good or bad, or what actions you're allowed to take. And the actions you take will affect how you move around the state space. So these two things kind of intertwine. And our job in reinforcement learning is to want to learn good actions. We want to learn good actions. Good. I'm going to put good in quotes. Good actions. Okay, and what does it mean for an action to be good? That is the third ingredient in reinforcement learning, is you have something called a reward function. A reward function. Okay. And a reward function is a number, just one number, not even a vector of numbers, that is positive when we're doing things that we want to do, and negative when we're doing things that you should not do. So positive is good, positive equals good, and negative equals bad. And this is a single number that tells you what is good or bad. A single number that tells you if it's good or bad. And so what is reinforcement learning? It is a method of when you are in a situation where you have a state space actions and a reward function, to learn what actions will lead to big rewards. So you're trying to figure out what actions lead to big rewards. If you are a robot, let's do an example. Suppose you are an engineer at the Roomba company, and at the end of cleaning up your room, the robot needs to make it back to the charging station. So then the reward function might be, how far away are you from the charging station? I guess it has to be 1 minus how far away you are, so like 1 over, because positive is good, right? So if you're very close to the charging station, that's good. If you're very far away, that's bad. If you take a long time to get there, that's bad. So you would bake into the reward function, you would try to steer, you'd say like, it's good if you make it to the charging station, it's bad if you stay away from the charging station. And then you could use this reinforcement learning stuff to automatically have the robot figure out, oh, okay, I just like move this way and then I find my way to the charging station. That's what I do to get a positive reward. In games, most games have something like points or like victory points. And you would just say, the reward is how many points you got in the game. And please try to learn how to play the game well so that you get as many points as possible. So in games, points are the reward. In the specific example I have over here, this is blackjack, which is a casino game. Who knows like vaguely the rules for blackjack? It's okay if you don't know the exact rules. So in blackjack, you are dealt 2 cards, and the dealer is also dealt 2 cards. But the dealer has 1 card face down, so you can only see one of the dealer's cards. And so what is the state space in this game? It is like, what is your cards and what is the dealer's cards? So for example, here I have ace 6 and the dealer has a 6. It turns out that you only need to know the sum of the cards. So an ace counts for an 11. So ace and 6 together is 17. So I have 17 and the dealer has 6.
Or 7.
Yeah, this is true. This is in real life, blackjack has all these like funny rules, like an ace sometimes counts as 1. And there's like rules about when you can split and stuff. Actually, later on in the course, we're going to do a simplified version of blackjack where it only has 1 thing. So this is true. Ace can be 1 or 11. in a real life casino. Yeah, you should not go to a casino with like a half-assed understanding of blackjack. You should really understand all the rules. Anyway, so you have some number, either 7 or 17, and it's your choice what to do next. You can either stand, which means you like stop getting cards, and then you're going to compare your number to what the dealer has after the dealer reveals their card and then takes their cards, or you can hit, which means you get another card. And if you get another card, your sum will go up, but if you ever go over 21, then you go bust and lose all your money. So that is standing and hitting. That's basically what you have to do in blackjack, is at every point you decide, am I going to stand or hit? There's also these other funny ones. Again, these are like kind of like weird exception rules. In a double, you can hit exactly one more time and you double your bet. So you have to put down more chips, but you get exactly one extra card. And in a split, again, something like weird happens. You have 2 copies of yourself. You pretend to be an amoeba or whatever and split into 2. So there's like funny things that can happen, but essentially it's stand or hit. Either do you want more cards or do you want to stop and compare to the dealer's card, and the person who is closest to 21 without going over is the winner. And the rewards in this case are very simple. They are how much money did you gain or win, right? And the reason this is important is because sometimes some of the bets have more payouts and less payouts. So like if you double the size of your bet. If you win in a situation where you doubled, that's twice as good as winning in a situation where you didn't double. So this is like a prototypical reinforcement learning problem. You have state space, which is what can happen with the cards. The actions are what do you want to do? And the rewards are very simple. Make as much money as you can, right? And a reinforcement learning algorithm would take in the rules of blackjack and observations about the state space and the action and convert it into learning which actions are the best to take. And in fact, people have done this on the internet. So if you go on the internet, you will be able to find, if you search for a blackjack strategy, you will find cards that look like this. And so on the x-axis here, it tells you what are the player's cards, and on the y-axis over here, it's what are the dealer's up cards. I guess I have x and y mixed up. Okay, the rows are the player's cards, and the columns are the dealer's cards. And you can just look up what is the best thing to do in every situation. So in our situation, we have ace 6, which is this row, and the dealer is showing a 6. So the dealer's up card is a 6. So we just look at what is the best thing to do, and it says the best thing to do is D double. So this is a situation where we're doing quite well. We should double our bet and take one more card, and hopefully we'll beat the dealer. That is sort of the optimal thing you can do. That is the action that will lead you to the most money. And people have calculated this out for all the possible states. What is the best thing to do in every situation? Reinforcement learning would do that automatically. So sort of people have done this by hand for this like relatively simple game. But reinforcement learning is how do you make a computer do this automatically? How do you have it come up with this table? And learn it over time through watching people play blackjack. Yeah?
Is this going to be posted later so I can use that?
Yes, this will be posted later. And in fact, a recording of the lecture should also be posted later, unless something goes wrong, which happens about once a term. Yeah.
We should do an educational trip to the casino.
Yes, well, this is something you can do. And in fact, last time I taught this course, the final project of the course was to make a blackjack like robot. Wasn't actually a robot, right? A blackjack algorithm that would decide how much do you want to bet and whether or not to hit or stay at every situation. And everybody in the course made their own blackjack thing. And then we had virtual trips to the casino. Not just one, but I think it was 100,000. So everybody would go to the casino 100,000 times. And then there was a leaderboard of how much money people had when they left the casino, right? And whoever has the most money at the end of the 100,000 trips to the casino, they were the winner. I haven't fully decided yet if I want to do blackjack again as the final project. But it might be this as your final project. Maybe I'll let you guys vote on it later. But yeah, so last year, this was the final project, was blackjack. Well, and it was modified I took away all the dumb rules that I don't like, because I'm the prof and I can do whatever I want. So I made aces always worth 11. And there were some negative cards to make it harder. Yeah, that was the final project. Was there a question over here, Gabe? Did you have a? No, okay. Yeah.
So does probability, because there's an element of chance to block.
Yes, absolutely, yeah.
So does that play a role in reinforcement?
Yes, so reinforcement learning is really intimately tied with probability, and it's in 2 ways. So in blackjack, there is explicitly probability because like even if you know exactly what is going to happen, the next card will be random. If you are a robot and you're trying to teach your robot to do things, even if there is some element of truth of if you knew exactly what was happening, you could figure out what things are doing perfectly. Things are sort of uncertain when you're learning it because you don't know yet. So there's probability baked in everywhere, There's probability, like real probability coming from the environment, but there's also your uncertainty is also represented there. So actually everything we do in reinforcement learning, we treat everything as probabilities. Either we don't even say, is it because it's really probability, or we just don't know. We just say, look, there's some distribution over the things that are going to happen if I take this action. Is that going to be good or bad? We're going to find out. And so yeah, it's very, very heavily probability based. Yeah.
Another question.
Yeah.
How good is it at finding the optimal solution or optimal strategy?
It is extremely good. That's the whole point is to chase down the optimal strategy. And in a game like blackjack, it will like do it like instantly. We're going to have 2 more examples where you'll see that it's really doing some amazing stuff of improving quite a lot. So that really is the idea, is like, can we formulate what does it mean to do the optimal strategy, even in the face of probabilities? And then can we like get close to it? Can we find ways to get close to that optimal strategy? And both of these things are like sort of what reinforcement learning is good at and why it's used. Yeah, great question. Yeah. Oh, this is a good point too, practically speaking, in the first week of class. Like if you have a very weak probability background, you will have to work and learn some probability. So like we're going to be doing expected values. I think at the end of this class, we'll have our first actual probability question that we're going to go into detail on Thursday. But like if you are missing a probability background, you will have to catch up on that in this course. So there's going to be a lot of probability. Okay, great comment. Any other questions? Yeah.
Does the reward function always take like the state space or an element of the state space as its input?
That is a good question. I think very technically speaking, it is the transition from one state to the other state that has a reward. But yeah, you should think of it as like we're in a state, we move to the next state, and on our way there, we get a reward. You'll see when we start to do this stuff in actual detail, there's like, we're gonna have an order. So we're gonna say like, first you move to this state, then you see the reward or like whatever. But yeah, very vaguely speaking, you should think of, you're here, I move to somewhere else in the state space, and on my way, I get a reward or a punishment or whatever. Yeah, great question. Yeah, in blackjack, you only get a reward at the end, right? So there's sort of like no rewards, like while you're playing, nothing is happening. And at the end of the hand, you're like, oh, look at me, I won. In other situations, you sort of continually get rewards. A very common one is trying to make a robot that like gets somewhere as fast as possible. And if you want to make your robot get somewhere as fast as possible, you give it a punishment. You hit it on the head with a newspaper every time it's not where it's supposed to be. And then over time it learns like, I should get there faster. So I get hit on the head less often. Yeah, yeah, great question. All right. Other questions? Okay, let's see another example, which I think is extremely exciting. It's chess and Go. And actually this came out in like 2017 or so. And this is part of what like attracted me to learning about all this stuff with reinforcement learning, is there is this, these people at Google, and they made a reinforcement learning algorithm that would play chess and Go. So Go is a complicated sort of game where you place stones on a board and you want the stones to do certain things. So probably less people have heard of Go, but most people have probably heard of chess. Who's heard of chess? Okay, great. So let's stick with chess as the example. So what is the state space actions and rewards in chess? Let's write them out. And then we'll play this little video about learning about this stuff. Okay, so this is example 1 was blackjack, and I did all the work for that and told you what it is. But example 2 is chess, and you guys can help me out. What is the state space? State space. What are the actions? And what are the rewards? Okay. Anyone want to take a stab at it? What do you think the state space in chess is? Yeah.
The location of the pieces.
Yeah. Location of pieces. Right. So you like walk over to the board, you see where all the pieces are. Every piece could be on one of 64 different squares. You write that down in some reasonable way. There's a knight on this square, there's a pawn on this square, and so on, the location of the pieces. Is there anything else? Yeah. Whose turn it is. This is extremely important. So I'm going to write this down with a times sign. This is how I think about this mathematically. Times whose turn it is. So this is like a Cartesian product. For every like picture of where all the pieces are, it could be white's turn, it could be black's turn, and both of those are possible. So it's sort of all the combinations of whose turn it is, one of two things, with all the places the pieces could be, you multiply them together. Those are the state space. This is essentially the right answer. Like, if you're thinking about this, where all the pieces are and whose turn it is, that's essentially what you need. A lot of times people forget whose turn it is. That is extremely important. So if you forget whose turn it is, nothing will work. Things will get all wonky. So last year, the final project was blackjack. 3 years ago, the final project was a 2-player game where people would take turns playing a certain game, and people would often forget whose turn it is, and then their programs would horribly not work. So if you forget this, then nothing will work. So you really do, this is super important. Super important when you're doing this. It turns out in chess, there's a bunch of extra dumb stuff that is extra, like technically, if you're a chess nerd, I'm gonna call this extra dumb stuff. That you technically, to be like fully correct, you do need to include extra information beyond where are the pieces and whose turn it is. Morally speaking, like this stuff is like kind of unimportant, and you can make a pretty good AI that like didn't know about this stuff. Does anyone know what are the extra dumb things you got to keep track of in chess to like fully know what is the state of the game? Yeah. That's how the different pieces move is not going to be in the state space. That's going to be in the actions. So you are right. You will need that at some point, but it's not in the state space. Yeah.
Well, you can only castle if your king and rook haven't moved. So move your rook and then move it back and it'll look the same.
That's right. So if you only know where the pieces are, you do not know whether or not the king has moved and then moved back. And so you technically do not know, is it a legal move to castle or not? And so one extra piece of information you need is something called castling rights. Castling rights. And this is like, is white allowed to castle right now? Are they allowed to castle on the king side? Are they allowed to castle on the queen side? And you need that for both white and black. So technically this is part of it. Again, in real life, you could make an AI that would like work. It just wouldn't be as good if you like left that out. So technically you need to know that. There's even deeper dumb stuff over here. There's even more dumb things. So I guess we're gonna figure out who plays a lot of chess. What extra dumb things do you need to know in chess? Yeah.
Well, since your king can enter in check, it's like how I gotta know if your king can be put into check in any way. Like you can't move a king in a certain way.
Right. Okay. Yeah.
It's
So
like check.
so which moves are legal? Those will be baked into
Oh,
actions. It is true that technically whose turn it is and where the pieces are related. Like if your king is in check, it's definitely your turn. Because you're not allowed to move your king into check. So it's not possible that you're in check and it's the opponent's turn. It's not something that can happen. So yeah, that will be part of actions, but is technically not part of state space. Yeah.
For en passant,
Yes.
you can do it to the very next.
That's right. So there's who knows who's heard of en passant? Okay, yeah. So en passant is like this weirdo, like, hey, this is like a weird trick you can do in chess where when pawns move in a certain way, on the move immediately after this like weird thing happens with the pawns, you're allowed to do a special move. Okay? And it's called en passant. It's like the weirdest part of chess. And because you're only allowed to do it the move after the weird thing with the pawns happens, you have to write down, did the weird things with the pawns happen last turn? Because if it happened 5 turns ago and the board is exactly the same, you're not allowed to do it. So I'm going to write down other weird stuff. And you can sort of ignore this. But it's like en passant. The other one is there's a rule in chess that if nobody moves a pawn for 50 moves, the game is a tie. So you technically also have to write down how many moves has it been since somebody moved a pawn, and if that counter gets all the way up to 50, the game is a tie. So there's a bunch of like other like weird things like this in the state space. There's like 3 move repetition and stuff. But essentially you just need where are the pieces and whose turn it is. This is like the important stuff. Okay, great, that's the state space. I think you guys have already figured out the actions are what are the legal moves. So you're given, it's your turn, you have all the pieces. The actions are all the possible legal moves you could take. And an action would be like, I'm going to choose to make this move. And you notice that an action will take you from one location in the state space to a different location in the state space, right? An action is like changing the values of the location of the pieces and whose turn it is, right? It changes whose turn it is by it's the other person's turn, and it changes the location of the pieces by whichever you moved. So the actions are essentially all possible legal moves. Legal moves. And that might be very complicated. So like, there's like pins and stuff, like certain pieces are allowed to move or not allowed to move under certain situations. So actually calculating all the possible legal moves is maybe somewhat computationally difficult, but in principle, those are the actions, right? Any legal move is an action and it will change which state you are in. So those are the actions. All right, last but not least, what are the rewards in chess? What are the rewards? Yeah.
Capturing a piece.
Capturing a piece. This is a great guess. I'm going to put it with a question mark. Capturing a piece. Yeah. Presumably you want to have capturing a piece is good, right? Positive. So let's say positive reward. And I'm going to put it with a question mark. Anyone else have any other guesses for what a reward is? Yeah.
Like putting the king in check in some way.
Putting the king in check, yeah. Putting
Your opponent's king in check. That's what
the king in check. Okay, let's say we're brainstorming. Let's brainstorm. So we'll put all of these with a question mark, and let's just get some ideas out. Okay, any other ideas? What else would be a good thing in chess? Yeah.
Not losing a piece.
Not losing a piece. Yes. Okay, this is great. So capturing a piece. Well, let's say like negative for losing a piece. Negative reward, because rewards can be positive or negative. Negative reward for losing a piece. So when your piece is taken, that's bad. Okay. Other ideas? Okay, so here's what I will tell you. When you are making a reinforcement learning thing, it is often up to you what you will make the rewards. So you could say, I'm going to try to solve chess. I'm going to try to think of it as a reinforcement learning problem. Here is my state space. Here are my actions. And I'm going to think of doing these rewards. And all of the rewards you guys have said are like good rewards that like your algorithm would learn to do whatever you told it. Like it would learn I should capture a lot of pieces. It would learn I should put the king in check. It would learn I should not let the opponent take my pieces. So whatever you say the rewards are, like by definition, those are the rewards. So it's not like these are wrong. However, the real benefit of reinforcement learning is that you can specify sort of like kind of abstract rewards, and the computer is supposed to be able to learn on its own these things. So you are kind of thinking like, I need to tell the computer that capturing a piece is good, and then it will learn to do that. Of course, if you tell it that capturing a piece is good, it will figure out how to capture a lot of pieces. But the beauty of reinforcement learning is that you can just like erase all this stuff and say, I'm not going to do any of this. I'm not going to do any of this. I'm just going to say the reward is you win the game. Win the game. Win the game. That's +1. Lose the game. That's -1. Lose the game. -1. And a tie is 0. 0. So you could do all this stuff, and the computer would learn to do exactly what you told it. But the beauty of reinforcement learning is you can also do this, and the computer will learn, I should just win the game. And all these things like capturing pieces being good, it will learn that sort of on the way to learning how to win the game. And this is why reinforcement learning is like important and valuable, is because you can sort of skip all of these human things, right? So of course for the game of chess, it kind of makes sense that capturing a piece is good or bad. But imagine it was like a robot, right? Like you're trying to tell the robot what is good and bad. Is going up a hill good or bad? Like you don't want to get all granular and say go up the hills, don't go down those hills. You just want to say like, hey man, like I need you over there by the charging station. Don't fall off the cliff. Like those are the things you want to tell it. And then it's supposed to figure out all the like up the hills, which motor to turn on. It's supposed to do that all on its own. And that is what reinforcement learning is supposed to do. You're supposed to be able to just give it like very broad instructions, and then it's supposed to figure out all this stuff on its own. And actually, it will do better, it will win more games if you do this than this, because probably when you tell it capturing a piece is good, you're not doing it exactly right. See, the thing is, sometimes capturing a piece is not good. Sometimes there's a way to sacrifice a bunch of pieces to win the game. And by telling it capture pieces, don't get your pieces captured, you have excluded all those ways of it to win the game, right? So not only is this hard to do, sometimes you don't even know how to do it, and you're going to misspecify what you actually want. So it's better to tell it this. And that is, in fact, what the people at Google did. So the people at Google, let's see, where are the people at Google? Here they are. So they did exactly that, and it was one algorithm that learned both chess and this game of Go. Go is a lot harder than chess because there's sort of like more possibilities that can happen. So in chess, computers have beaten chess since like the late 90s. Computers have been beating like the best humans at chess, but they have used a lot of like heuristics, and we have told the computers things like taking pieces is good, you know, situations like that. So like all of these things went into the computers like Deep Blue that beat the best grandmasters in the late 90s, but the Google people did this. And then the computer learned all on its own how to do chess. And let me show you this little clip of a video of this Google guy talking about it. And in fact, he's going to talk about Go. And Go is the exciting one because nobody had beaten Go or had beaten like top Go players since then. Is this a video? It's not going to work. Okay, let me take a minute to get the video, and then I will play the video for you. Let's see if I can find it. Okay, so that was David Silver talking about their AlphaGo 0, and it learns from scratch. So the only thing that was fed to it is exactly what I had on the board, which is that we told it what does a win mean, we told it what does a loss mean, we told it what are the allowed moves, like what are the actions, and it figured out how to play the game all on its own. And later on, years later, that video was from like 7 years ago, they have applied it to things like StarCraft, like things where you don't have perfect information, all sorts of complicated things. Nowadays, people are applying it to robotics and stuff like that. So this is like the hope of reinforcement learning, is that you can kind of like, in any situation where you can say what is good or bad, you should be able to translate that into, can you figure out the good actions to take and the bad actions to take, even if they're sort of like pretty far removed from the good or the bad. That's the hope of reinforcement learning. Let me give you guys 2 more quick examples before I wrap up the class. Okay, example 3. I'll do this one very quickly. This is a paper from the company Lyft. Lyft is like an Uber competitor, and they use reinforcement learning to match drivers and what do you call somebody who takes a ride? Riders? Riders and drivers. Okay, so when you press I need a ride on your Lyft app, then on the app of one of the drivers, it will appear like where you are and to pick you up. But how does that matching happen? And here's an example they gave in their paper. So this person requested a ride at 6 p.m. This person requested a ride at 6:01 p.m. And here are 2 drivers that we have. How should we assign the drivers to the riders? And in this situation, you can sort of see by looking, okay, probably A should go to 1 and B should go to 2. But like, how do you know to do that? And they used a reinforcement learning algorithm to sort of like take different parameters on like how people's preferences and turn that into a matching of how to do it. And part of the reason it's very difficult is it's very time dependent. So they have a little table here. In San Francisco, sort of in the morning, it's kind of the opposite of the afternoon. So people are all going one way or going the other way, and your algorithm has to learn like, oh, in the morning, do it this way, in the afternoon, do it that way, and it's kind of the opposite of each other depending on time of day. And the nice thing is it sort of does it all automatically on the fly. So this is an online reinforcement learning algorithm. Online means it's sort of constantly running and constantly improving itself. So every day it's doing these matchings, and it's learning from what's happening and improving for the next day. So that's kind of an industrial example beyond a game or something. The last example I'll tell you today is, it turns out what I said before about GPTs, the big innovation in ChatGPT was to take a GPT and improve it with something called RLHF. And RLHF stands for Reinforcement Learning with Human Feedback. And the problem that is being solved here is described in this top corner over here. Let's see, can I zoom in? Probably not. Okay, so hopefully you guys can read this. So it turns out if you take a GPT and you type in, explain the moon landing to a 6-year-old in a few sentences. So remember, what does a GPT do? It tries to predict the next word. And it repeatedly predicts the next word based on what it has seen on the internet. So if you type in, explain the moon landing to a 6-year-old in a few sentences to just these GPT models, and in fact they have an example, this is GPT-3, which was like a state-of-the-art model like 3 or 4 years ago, what will it output? You might think it will tell you the answer because you're used to ChatGPT, but it will not tell you the answer. What it will do is it will start listing questions to ask a 6-year-old. So it'll say, explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old in a few sentences, explain the Big Bang Theory to a 6-year-old, explain evolution to a 6-year-old. And what it is doing is exactly what it was trained to do, which is, if you see the sentence, explain the moon landing to a 6-year-old in a few sentences, on some article somewhere on the internet, what would be the next line of that article? And it turns out that like it's very likely that it would be an article with a list of questions, and the GPT is like, after this question comes this question, and after that question comes this other question. So it's not answering the question at all. It's just predicting what would be on an article that has this question in it, and what would be on an article that has this questions in it is more questions. So that's not very useful. So in fact, the big thing that made ChatGPT like exciting and like brought it like mainstream is they had this method called RLHF, where they were like able to bend the will of the GPTs to answer questions. And the way they did that is with human feedback. So these guys at OpenAI, I won't give the full details here in the interest of time. They have a very nice article. So if you click this link, which I can also post, all this stuff is explained sort of in a nice blog post. They paid people all over the world to, first of all, answer questions. So answer questions like this, to give examples to the GPT to try to make better answerers. And then using the answers, they came up with these, they also had people rate which is a better answer. So like you have a bunch of different answers to this question, and the humans will say, oh, that's a good answer to the question. That's this kind of thing where you just list more questions, that's a terrible answer, don't do that. And then using those two things, they did reinforcement learning using what the humans said as the reward. So the reward was, did the humans say this was good, or did the humans say it was bad? And just using that signal of, please do whatever the humans say is good, then they were able to take GPT as a starting point and tune it a little bit to make ChatGPT, which answers the question with, people went to the moon and they took pictures of what they saw and sent them back to Earth so we can all see them. So you can sort of take something that was trained with self-supervised learning and just like modify it a bit with reinforcement learning at the end to like put on any reward you want. And in this case, the reward is whatever the human said was good, right? So this is something you can do, and this is called RLHF. This is what makes the chat in ChatGPT. Okay, so that's my last example of reinforcement learning.